Okay, record.
Hi- Okay, perfect. Okay, hello everyone. So my name is Arjun. I use they, them pronouns. I am a final year PhD student at UCLA, and today I'll be talking about my work, theoretical and empirical insights into the origins of degree bias in GNNs. And yeah, thank you so much to the organizers of the reading group for having me. So a little bit of motivation about why we're even doing this work. So we know that machine learning systems and applications have really proliferated over the last decade. And there's kind of two main ways in which this is manifested. One is in the form of powerful user-facing products. We see a lot of chat-based applications like ChatGPT and Claude, as well as things like Adobe Neural Filters, which are kind of deep learning-based tools that help people edit images without like low-level edits. On the other hand, we see that machine learning is being used at scale to make predictions about individuals. For example, Snapchat and Google both do targeted advertising, and they try to infer characteristics of individuals to improve the ads that they receive. And companies like Amazon have in the past used automated hiring systems based on machine learning techniques to rank resumes, to filter out applicants. So we can see that there's kind of like multiple sides to this proliferation. One is in the side of maybe things that are more public facing, like these applications, like chat-based applications. And on the other side, we maybe have a lot of opaque predictions that are being made about us behind the scenes. At the same time, there's a lot of skepticism about the ethical conduct of AI companies. We actually see that the skepticism is growing according to the 2025 Stanford AI Index report, and the trust and fairness of AI is decreasing. In addition, 34% of the people surveyed by this report found that equity and fairness was a primary concern for them, but only 26% of them felt that it was being actively mitigated. So unfairness issues in machine learning do, in fact, cause real-world harm. We may ask, like, why are machine learning models unfair? This is just, I don't know who's attending the meeting, so just in case. We see that a lot of times marginalized social groups are underrepresented or misrepresented in the data on which models are trained, but also model design choices contribute quite a bit to the ways in which bias is encoded or amplified by models. A very quintessential example of this phenomenon is the gender shades paper, which showed that commercial facial recognition technologies perform significantly worse for darker skinned women than for lighter skinned men. And this has real world impacts. Again, I want to emphasize that whenever we do this fairness work, we want to connect it back to what is the effect on social inequality. So if the police, for example, is using facial recognition tools for doing criminal recognition or like suspect recognition, uh, these tools do have a higher rate of misflagging Black individuals, and particularly Black women, as being criminals, and this puts them at increased risk of police brutality and questioning. So to kind of summarize all these things together, as ML models are increasingly deployed to make predictions about humans and their relationships at scale, it's imperative that we make sure these models are fair and do not amplify social inequalities. Another kind of important point here is that in modern machine learning models, we tend to be processing context a lot. In particular, for graph neural networks, when they're applied to things like social networks, we process social context. So in the bottom here, we see an example of a social network. This could be something like LinkedIn, and companies often may leverage the professional connections that an individual has to improve kind of prediction about whether they should be selected for a job. So we may have these two folks here who are job applicants, and based off of like their past work experience as well as their proximity to other individuals within a network, companies may make predictions about whether they're a good fit for a company, whether they're a good fit for a role. And GNNs are quite prevalent. I think sometimes I've heard people say that like GNNs don't really have any like industrial use case, or they're maybe not as like visible to folks as maybe people working in the field would think. But actually, quite a few companies are using it in deployed systems. So companies like Uber, Google, Alibaba, Pinterest use GNNs for product recommendation and content discovery. And Twitter, in their words, use GNNs for personalized ads rankings, account follow recommendation, offensive content detection, and search ranking. On the more academic side of things, we see that, well, this data is a little bit old, so it's from 2022, but it's also true for 2023. We see that GNNs were the third most popular keyword in at iClear. So I want to give a little bit of background as well now for people who may not be as familiar with GNNs. What does the input look like? What does the output look like? So for inputs, we know that we have a graph which comprises of vertices and edges, and we also have some node features. So each node has its own set of features. We also have an adjacency matrix that represents the connections between different nodes in our graph. And then the way that a GNN technically works, or at least the way we're going to set it up, is we have an encoder that can compute node representations based off of the node features and the adjacency matrix. And then these representations, again, at least for the sake of our presentation, can be used for node classification or link prediction. So for example, in the case of a social network, we may use a GNN encoder to get representations of different users, and then those representations may be used downstream by a company to make to target advertisements to a person in the network, or maybe recommend that they should follow somebody in the network or make connections between individuals. But there are some harms that come from this network nature of machine learning. So if a company uses existing social media connections to recommend new connections within a social network, this can actually reinforce echo chambers. It can also further suppress peripheral accounts within our social network. And actually, this has been not documented in the case of GNNs necessarily, but on Instagram, this is a really great paper by Stoica et al., 2018, called Algorithmic Glass Ceiling. Like accounts on Instagram run by women have a much lower number of followers than accounts run by men. And the Instagram recommendation algorithm can actually reinforce that. So it may get a signal that accounts run by men are deserve to be followed at a higher rate, and further isolate or sideline accounts run by women. We can also see that if financial institutions use the existing financial connections that an individual has to assess things like credit worthiness, economically disenfranchised black loan applicants because of historical inequity can be further isolated from the rest of like the financial network, and their applications for loans can be rejected. In addition, this is the same examples that I provided earlier, but if we're using existing professional connections to filter job applicants, professionally isolated women job applicants can be rejected. So again, consider like this LinkedIn-esque network where we have two applicants, and you may have different numbers of years of prior experience working in a similar role, but you may be selected even with fewer years of working experience because of your proximity to existing employees in a company, and that may be deemed as you having better fit to the company and may be deemed as you having like closer a set of skills. But if you're further away in the network from existing company employees, you may not be selected for this role, even if you have more years of work experience. And what's interesting about this, according to the Boyd et al. 2014 paper, is this is actually not illegal. So in the state of California, there are many different protected attributes with respect to which you can't discriminate when you're making job decisions, but network proximity is not one of them. But we can actually see in this example that network proximity is often a proxy for things like gender. So we can see that the unfairness of GNNs is exacerbated by social context. So things like the neighbors that an individual has, the communities that they're a part of, as well as the message passing schemes that GNNs use. And these issues really are not explored in research on the fairness of traditional machine learning and require a deeper principled understanding. So that's where this paper comes in. Now you might be wondering, like, I've given a lot of context, and hopefully that was helpful for people who may not be as familiar with this area, but now I'm going to do a deeper dive into the paper that I was invited to present in particular. So GNNs exhibit better performance for high degree nodes on node classification tasks. And you can see in the figure to the right that as the degree of our nodes is increasing, that our test loss on those nodes decreases. And this is not great because it privileges high degree actors and marginalizes fringe users in social networks during things like social recommendation. If we're recommending content to them or recommending connections with other individuals within a social network, we can see that if we have more brittle representations, for example, for low degree nodes or worse performance for low degree nodes, they're not going to be served as well by our algorithms. An example of this is maybe we're predicting whether a health advisory should be shown to users in a social network. And if we have the marginalized LGBTQI plus users in a network who have like few connections to other individuals within the network, there's going to be poor advisory visibility for those individuals and then increased health disparities because they're not getting the announcement that maybe they should go out and get a vaccine for a particular epidemic. And so degree bias has been quite well studied. There's like a lot of hypotheses for why GNN degree bias occurs. And we did a survey of 38 papers finding that these hypotheses actually are often not rigorously validated and can sometimes even be contradictory. So just to read some of the hypotheses that we found, the top ones, people posited that neighborhoods of low degree nodes contain insufficient or overly noisy information to learn effective representations. Another hypothesis was that high degree nodes have a larger influence on GNN training because they have a greater number of links with other nodes, thereby dominating message passing. And the last one that I'll read out is high degree nodes exert more influence on the representations of and predictions for nodes as the number of GNN layers increases. And I think some kind of things that popped out to me and Jian and my advisor, Professor Sun, as we were doing this work, was that there seems to be kind of, maybe for one, not a clear distinction between training versus test time factors in degree bias. So, like the first hypothesis H1 makes no mention of training, while the second hypothesis says that it's because of the fact that high degree nodes dominate training that degree bias occurs. And then H3 suggests that you need to have a deep GNN in order to have degree bias. But in fact, we find in our work that you don't really need necessarily a deep GNN for this to happen. And it's not always a result of training time factors that we have degree bias in practice. So our two research questions that maybe you can keep in the back of your mind as we're going through this work is it possible to analytically link a node's degree to its GNN test and training error in the semi-supervised learning setting? And which mechanisms, for example, the graph structure or filters, give rise to degree bias? So I'm going to set up the scene a little bit notationally. We have our graph structure A and our node labels, which are fixed. So basically, we're given our graph, which is fixed, and we're given our node labels, which are fixed. And then we are going to get node features by independently sampling. In our case, it's arbitrary feature distributions, but each class has its own feature distribution, and we're just going to generate features by sampling from a class-specific distribution. We also are going to use a cross-entropy loss function, which basically computes a loss for node I with respect to a particular class C for model M that outputs predictions. And we're going to be doing everything in the semi-supervised learning setting. In particular, we're going to be training M with the full graph, so all the node features in the entire adjacency matrix, but only considering a labeled subset of nodes S. That is part of like the total set of vertices. So the first theorem we have is we're going to consider a test node I with label C. And now we're going to do the counterfactual. We're going to consider a label C prime that's not equal to C. And we're going to look at the probability that our loss for node I with respect to class C is larger than the loss of node I with respect to class C prime. And we can think of this as the probability that the model M misclassifies I, that the loss like with respect to the correct class is higher than with respect to the incorrect class. Then under some mild assumptions, we can show that this probability is upper bounded by 1 over 1 plus this variable r, which I'll get to in a second. I want to emphasize that at this point, so far, we haven't made any assumptions about what the model is. It could be a GNN, it could be an MLP, logistic regression model. And this variable R is what we call the squared inverse coefficient of variation. That's a mouthful. So the definition is here. It basically looks at the difference in representation, the expected difference in representations between like like for node I with respect to like C prime, like the logit for C versus C prime, but normalized by the variance of the difference in representation. So we're basically looking at like what is my representation for node I logit C prime minus like representation for node I logit C. How big is that in expectation? And then can we normalize that by the variance of that difference? And I'll show a picture in a second to make this whole thing a little bit clearer. But I want to also mention that this is a related. You need to like take the reciprocal and then not take the square. But it's also a normalized measure of dispersion that's often used in economics to quantify inequality. Yeah, so I think this picture makes it a little bit easier to understand, and maybe even gives a suggestion of like what degree bias may occur or why it may occur. So this was a PCA plot that we made of the representations of nodes from produced by a trained GNN. And so the X's here represent low degree nodes, and the circles represent high degree nodes. And we can already see that looking at this plot, the low degree nodes have a little bit more variance with respect to their class centers than the high degree nodes do. So you can see that the circles are more closely clustered together, and the crosses are more spread out. And so basically here what we're this kind of like, has a relation to the theorem that we just mentioned before, because what we're saying in the previous theorem is that the probability of misclassification is reduced when the representation for a node I is further away in expectation from the decision boundary and has low dispersion. And exactly like in the theorem here, what's actually happening is like we can see that when we're further away, when the expectation is larger and the dispersion is really low, then this quantity gets very small, the right-hand side, and then our probability misclassification gets very tiny as well. Okay, now we're gonna jump in a GNN world. So suppose M is an L-layer general message passing GNN. So here we see that our Lth layer node representations are the result of applying a nonlinearity to our pre-activated representations, which takes the form of some self loops. So we're just using the previous layer's representations and then doing a transformation. We also are going to consider our node information. This is like the whole reason we use a GNN, right? Like we have a graph filter and we're aggregating the representations from the previous layer in some way and then transforming them. And then also residual connections. So we consider like the initial node features as well, and inject them into each layer's representations. There's a lot of different choices that we can make for this PL, the graph filter that we're using. There's a random walk filter, which is basically just row normalization of the adjacency matrix. There's also the symmetric filter, which is related. It's very spectrally related, at least to the random walk filter, but it has the benefit of being a symmetric matrix. And then this one is like, if you're not familiar with this, don't worry about it, but it's just an attention, like the GAT filter, the graph attention network filter, where we're basically learning an edge weight. We're learning an edge weight like between every pair of nodes that's connected in the original graph. And the important thing here, I think like my favorite part about this paper, kind of from a narrative perspective, is that graph machine learning practitioners make choices about which filter to use in practice. And that actually has a large impact on the ways in which the model behaves. But I think oftentimes, with respect to fairness at least, and I don't think a lot of times practitioners are thinking about those consequences for fairness. So we're going to make some simplifications. I think it's always good to make simplifications to get more out of your theory and state those assumptions up front. But we're going to simplify our model RW, which is basically the abbreviation we're going to use for the version of this model that uses the random walk filter. And we're going to choose all the nonlinearities to be identity functions, or the activation functions to be identity functions. So there's going to be no nonlinearities in our model. And we're going to collapse the whole thing. So we can actually see that we get a closed form expression for this that's no longer, I mean, we had closed form expression before, but like now we don't have this whole like iterative definition or recursive definition of the representations. For our model, we just can write everything in terms of x, a single set of weights, and different powers of our graph filter. And our goal again is to prove a lower bound for uh, this measure of inequality, RIC prime, or coefficient of variation, because we know that a higher R will lead to a lower misclassification probability. And this is the formula again, in case it's been a while. So the probability of misclassification is upper bounded by 1 over 1 plus R. And we want to prove a lower bound for this because we know that if we can push that lower bound up, we can reduce the probability of misclassification. And so what's interesting about this general purpose GNN, so this is actually just for the random walk case, but I'll get to the symmetric case in a second. But if we can, should we know that the variance of our predictions is upper bounded by some value m, then we can actually we can write this lower bound out, and it depends on two factors. One in the numerator is what we call the prediction homogeneity, and the other one is what we call the collision probability. So I'm going to dive into the definitions of these. The first one is the prediction homogeneity. And what we're looking at basically here is if we take, it basically measures at a high level the expected prediction scores for all the nodes J in a network, weighted by the probability of that node being reached by a length L random walk starting from I. So we're going to take the expectation over all the nodes in our kind of random walk L-hop random walk distribution starting from I, and then take kind of the expectation over all the features that they could possibly have, and look at the prediction score, and here like this WL C prime minus C is the boundary that separates classes C and C prime. So it's how much more likely are each of these nodes based on their features uh, to be predicted to belong to class C prime versus class C. So basically, we can see that like for a more negative value, that the nodes are predicted to have the same label as node I, but for the more positive value, they're predicted to have a different label than class I, or sorry, than node I rather. Are there any questions about this definition that I can answer? I'm also happy to take questions at any point during the presentation.
No, you're good. Makes total sense.
Okay. Yeah, so to kind of emphasize what I just said right now, to make this RIC prime larger, it's sufficient that this prediction homogeneity value is more negative. That basically means that all the nodes in our L-hop random walk distribution are that have at least some probability mass are the same class as node I. So basically, there's two ways that that can happen. Like one, when there are more nodes in the L-hop neighborhood of I that are also in class C or are part of the training set S. And I think this is kind of where there is a slight distinction between homophily and like this prediction homogeneity coefficient. I completely think that homophily is the biggest factor here. So basically, like if homophily is when you have a node, like when you're a node and all the nodes around you in your L-hop neighborhood also share the same class as you. So that clearly definitely makes the prediction homogeneity value more negative, and that's really good for reducing a misclassification probability. But actually, also, if the nodes in our neighborhood are part of the training set, like then we know that we're doing really well on them because we already fit to them. And that also reduces our prediction homogeneity. So I think there's like it's homophily, but also kind of a little bit spicier. There's like an additional factor here that we are considering.
Sorry,
And I
I
think
have a question before you
yes.
continue. I think I don't fully understand why it would be negative if they're all similar. I thought it would be negative if they were all different. Maybe I'm misunderstanding something.
Yeah, no, I think it's mostly just the choice that I made, which I actually kind of regret a little bit, and I wish I flipped. the WC prime minus C. So basically, like because it's the weights corresponding to logit C prime minus the weights corresponding to logit C, it's more negative when all of the nodes in that neighborhood are also belonging to class C, which is like the class that node I has.
I see, I see. So it's the probability that they are misclassified, but actually, so WC prime would be the probability that they're misclassified.
Yes.
Okay, and since they are all the same, that probability, okay, I understand. Gotcha.
It's a great question. Yeah, it's like the probability that well, yeah, it's not necessarily the probability that they're misclassified, but the probability that they're given the wrong class for node I. So it's more
Hmm.
about how similar they are to node I rather than like how much that they're misclassified themselves. But I think it is a little bit confusing that the C prime minus C is kind of flipped a little bit. So like here, when there's more, like when the weights for C like produce like a larger inner product with the features in the L-hop neighborhood, the whole quantity gets more negative. And then that means
Gotcha.
that they have the same label as I, or the same like predicted label as node I.
Gotcha. Gotcha. Thank-
And a little kind of empirical validation here is that degree bias does not occur for heterophilic networks. So this is for either the squirrel or chameleon data set. I don't remember right now, but we see that we don't get that nice trend where as the degree increases, the test loss is decreasing. And that's because, at least, what our theory predicts is that's because for like, for the different nodes, the prediction homogeneity is not negative. It may be like quite close to zero because you have nodes belonging to different classes in your L-hop neighborhood, or maybe it could be super positive even because like, you're um, like all the nodes in your neighborhood are like the different class than you entirely. The other quantity that we talked about earlier was the L-hop collision probability. And this one is very cool. I think it's like a very nice kind of way of quantifying diversity. It basically quantifies the probability of two length L random walks starting from node I and colliding at the same end node J. So we can see here in the figure, like if we have, um, I think actually any of these would work as a starting point. But if we take like this red node as our node I and we look at the probability of two nodes colliding, it's basically if we can like look at all the L equals two random walks that start at this red node and see the probability of them ending up at the same end node. And when the collision probability is lower, that means that the random walks are more diverse. Basically, the random walks are diffusing a lot more. But there's like a lower probability that they end up at the same end node. So we can also see based off of our the stated theorem that to make this coefficient of variation larger, it's efficient that our inverse collision probability is larger. So basically, our probability of collision is smaller. And what this means is that when, or I guess like if we take a specific example, when we have like one layer in our network, this is we can write this out more explicitly, and it's very close to very close to being just the degree of the node, and obviously that's like much larger for high degree nodes. And I think the nice intuitive understanding to take away from this is that basically like a larger inverse collision probability indicates a more diverse and informative L-hop neighborhood. And that helps a lot with reducing this probability of misclassification.
You have
So
another
again,
question. I'm so
yes.
sorry.
No, no, go for it.
So you said that it's like a measure of diversity, but to me it sounds a lot like a measure of connectivity. Like the idea of the sparseness of your graph versus the denseness of the graph. Because if that value is really high, if the graph is really dense, then the probability of collision seems like it would be really high. But if the graph is sparse, then it seems like it would probably be low. Is that a correct intuition?
I think, yeah, I think that also is, I think it's definitely correct. And I think it's like part of like the broader measure here. I think you're completely correct that it's diversity in like, or at least the way that I'm describing diversity is in terms of graph structure. Because exactly as you said, like there's no kind of like there's no feature information involved in this measurement at all. It's just purely based off of like the random walk structure of the graph. So it has a lot to do with sparsity and probably also related to like the bottlenecks like in the graph as well. But I think yeah, sparsity and bottlenecks, I'm like kind of describing the whole thing in some ways as like the structural diversity, like your local context structural diversity within the network.
Gotcha, gotcha. Thanks.
So just to revisit the figure from earlier, I don't have much more to say about this figure, but basically we showed theoretically, and we have some intuition now that like low degree nodes have a higher dispersion in the representation space of this GNN because of the filter choice, because we're using these random walk filter. There's the variance of these low degree nodes is quite high, and their distance from the well, actually, their distance like from like the decision boundary compared to high degree nodes may not be that different in expectation, but that comes down more to like the homophily properties of the networks with their association with node degree. But I think the bigger thing here is just to know that low degree nodes do have a higher dispersion, and that actually has an impact on like how well the model performs on downstream tasks, such as node classification. So I just provided some like, kind of maybe seemingly cherry-picked examples here, but we do validate these theoretical findings on three convolutional filter choices like the random walk filter, the symmetric filter, and the attention filter, and eight real-world network data sets covering diverse domains. And we confirm that degree bias does not occur for heterophilic networks, as predicted by the theory we propose. In addition, this inverse collision probability is positively associated with node degree, and low degree node representations tend to have a larger inverse coefficient of variation, which doesn't necessarily make the probability misclassification higher, but it doesn't suppress the probability misclassification as much as a high degree node. So now you might be wondering, what about SIM, like the symmetric filter? Like we only talked about the random walk filter so far. And when I looked at this, I was a little bit like confused because the PCA here shows that actually the low degree nodes are quite close to the decision boundary, but they also are more tightly clustered. And that's very different from the previous image, which showed that the low degree nodes were more spread out, had more dispersion. So what we actually I'm not going to get into a lot of detail here, but what we can actually find is approximately the coefficient of variation, both the numerator and the denominator are scaled by the degree of the node. And so basically the numerator and denominator, that factor cancels out, like the degree of the node cancels out, and we end up in effectively the same situation as with the random walk filter, where even though the low degree nodes are closer, because they're closer to decision boundary because they have like a lower variance, like those two factors eventually even themselves out, and then we end up with the same issue where the dispersion after doing this normalization is still much higher for low degree nodes, and that leads to a higher misclassification probability. So far, everything has been kind of the degree bias discussion we've been having in the graph neural workspace. But there's another kind of thing that we observed that there are discrepancies in training during when you're training a GNN between low degree nodes and high degree nodes. So if we look at the figures to the left, we can see that when we train a GNN with the random walk filter, as you increase the number of epochs that you're training for, see like roughly the high degree nodes and low degree nodes have like a relatively similar decline in training loss. But then for sim, as the number of training increases, the high degree nodes have their loss dip a lot faster than the low degree nodes do. And so I think like one thing we end up proving in this paper is that during mini batch gradient descent, like sim may adjust its loss on low degree nodes more slowly than on high degree nodes compared to RW. And I think this is kind of the important thing to emphasize. I also am not going to get super into it today, but it's not always the case that the low degree nodes and high degree nodes have their loss drop at the same rate, because it also depends on how similar your neighbor's features are to features of nodes in the training batch, of course. But basically, the point we make is that compared to RW. So if you use RW as the baseline, then we can actually see a bigger gap between the low degree nodes and high degree nodes for the GNN where we're using a symmetric filter. You might wonder, why do we care? So like test time stuff clearly cares because we're like deploying these systems out in the real world. But training time is like whatever. It also seems that that like the loss evens out, right? Like at the end, everyone has the same like pretty good loss if you're part of the training set. So why do we care? As GNNs are applied increasingly to large networks, only a few epochs of training may be possible due to limited compute. So I have heard through like the networks that like some companies will have enough uh, compute to train their like GNN for two epochs because their networks are like so immensely large. And you might wonder like if that's not complete training, if we don't have the compute to train for 1,000 epochs, which nodes then receive superior utility from this limited training? And also, GNNs may be serving as an efficient lookup mechanism for nodes. We see a lot of things like neural hashing, where we may embed nodes in our network and then try to do lookup based off of how good the representations are for the nodes that we learned the representations for. And if these representations are partially trained, we can perform a lot more poorly for low degree nodes. Yeah, so just to kind of talk about the theorem very quickly, we show that the change in loss for a node I after an arbitrary training step t, so basically like the difference between the loss at step t plus 1 minus the loss at step t for this modeled symmetric filter, uh, it depends on the square root or is upper bounded by the square root of the degree of the node. And it also depends on the similarity between the neighbors of node I and the nodes in our training batch. So basically, if the neighbors of node I have very similar features to the features of nodes in the training batch, then that's great because we stepped in the feature direction towards kind of an area of the weight space that works really well for us, like our neighbors, for like me as a node. But also how large that step is depends on the square root of my degree. And I'll show the visual again in a second, but just the big takeaways from this theorem is that the change in loss after this training step has a smaller magnitude if I is lower degree, and the loss for I changes more slowly when the features of nodes in our neighborhood are not similar to features in the neighborhoods of nodes in the training batch. So this is not what I intended to do. I'm gonna go back here. So this kind of figure illustrates a lot of what the problem is. We can see that high degree nodes have a much higher magnitude and representation space than low degree nodes do. And what this ends up entailing for our learning process is we take larger steps simply because of the magnitude of the representations of these high degree nodes. And the magnitude is because of the way we do this normalization, because the normalization is symmetric. We don't actually, like, unlike the row normalization, we don't have a degree independent scaling of our node representations. We end up having representations that are scaled approximately by the square root of the degree of the node. And you might be familiar with work that talks about how why feature normalization is important, like why all it matters that all our like data is on the same scale, and that's just very intimately connected to this. Like we want all our data to be on the same scale because otherwise we take really large steps, or like very disproportionately sized steps depending on like what data we're using during training.
Sorry, I have another question.
Yeah, go for it.
Okay, so there was a slide. I'm afraid I don't remember the numbers, but there was the random walk and there was the symmetric, and you could see, go back. You were just there a second ago.
Oh,
I'm so
sorry.
sorry. You can see the loss curve, and you were basically saying that for the symmetric version, exactly this one, for the symmetric version, the training loss adjusts itself more slowly for the lower degree nodes. But
Mhm.
as far as I understand from what you just said, right, where you were talking about how the symmetry, the fact that we normalize by the degree, this is actually and then you went to show the PCA, you actually showed that there is a less noticeable difference in the features for this symmetric versus the random walk. So I'm a little confused about the difference between those two outcomes.
Okay, yes. So, sorry, could you like repeat again this part? Like you said there's a
Yeah,
difference in
so
features.
here it seemed like what you were saying was that the reason, like the normalization is actually a good thing. But then if the normalization is actually a good thing, then why is it that the random walk doesn't seem to have as many lags in the lower, like in the updates for the lower
Mhm.
degree nodes?
Yeah, so maybe I can clarify a little bit. I think this is there's two different kinds of normalization. The one that I was referring to here is the adjacency matrix normalization. So like the fact that we do symmetric normalization on the adjacency matrix means that when we do the multiplication with the features, the features for high degree nodes just have a larger magnitude, which I think that part is probably a little bit clear. But then what I was referring to afterwards is that if we treat a times x, or like the normalized version of a times x as our features, then we can think about like how that goes against all the like instructions that we've received as machine learning people to like normalize our features. So like if like a times x is like now our new input features to like our model, then like all the nodes have, or like yeah, the nodes have different scales or
I
different
understand.
magnitudes for their features.
Gotcha. Makes sense. Thanks.
Yeah, yeah. Feel free to like yeah ask questions at any point. Like don't apologize at all. I probably like misspoke like multiple times during this talk, so you can always like feel free to clarify things. Yeah, this is just kind of like a little bit extra confirmation that I was really interested about this. So I think it may feel like a tangent, but you can always like feel free to like talk to me more about it. I think the expressive power stuff in GNN is quite interesting. But oftentimes like the expressive power, it gives you a good upper bound on it's like the maximum possible training accuracy you can achieve. And the way you can create like a Westphill or Lehman based classifier is basically doing like this WL hashing for all the nodes in your network. And then all the nodes that have the same hash, you can just pick the majority class among those nodes and then use that as your prediction. And so I just kind of wanted to see if like like the Westphiler Lehman test was like actively like because it's upper bound, if it's very low, then that could be kind of a possible cause of this training time degree bias. Well, we found that in all the networks empirically, so this is not theoretically, but empirically, the training like nodes are quite easy to distinguish in practice. So it's almost always possible to get like a 100% training accuracy. And even when it's not, it's because like there just happen to be these like extra duplicate nodes in a lot of like the benchmarks that we use like in graph learning. And then also if I looked at the mean absolute gradient for a model as we get close to the end of training, it's very small. Like the scale here is 10 to the negative seventh. So it's basically like getting a zero gradient, like the losses converge. It's like very small for all the nodes. So I don't think that if you like have enough steps of training, this discrepancy empirically seems to kind of go away. I think obviously if you want to prove that more formally, you'd have to make some assumptions about like the regularity properties of like the adjacency matrix and like what like the dynamics of the model, like probably improve. I know it's like notoriously hard to study training dynamics for like most neural networks. You have to make some simplifications, but that's always something interesting to study. So if you want to study like the convergence properties of these models, I'm sure people have started doing that or maybe have already done it, and you can also contribute in that space. Yeah, so I think like the scope of our paper is more about just kind of trying to understand why this happens. So we didn't propose any explicit solutions, but we provided like a roadmap based off of the theoretical findings to hopefully alleviate degree bias going forward. So one thing is to maximize this inverse collision probability of low degree nodes. And if you want to translate that into something that you can actually operationalize in practice, that could mean augmenting edges for low degree nodes. As Rebecca said, right? Like maybe you want to decrease the sparsity of the network. And so you can add edges to low degree nodes, make sure that like these low degree nodes aren't as isolated. And there's more ways for these random walks to diffuse so that we have more structural diversity. We can also increase the LHOP prediction homogeneity of low degree nodes. And that means ensuring similar label densities in the neighborhoods of low and high degree nodes. So remember, I think as we said that The prediction homogeneity can become more negative if there's one homophily, but then also the fact that you're doing really well at predicting the correct class for those nodes in your neighborhood. And so if there are more nodes in your neighborhood that are part of the training set, then you end up getting a better prediction homogeneity. And so maybe ensuring that you have a good number of training nodes in everyone's neighborhood, especially low degree nodes, can make the prediction homogeneity more negative, and improve degree bias. There's also things we can do, maybe more post-processing, so we can minimize distributional differences in the representations of low and high degree nodes. I think this is like the thing about like we just discussed around like feature normalization. So we can almost do something like batch normalization of the last layer node representations and start matching like the distributions of nodes representations together. And some people have already done this, I think, like have kind of tried to do some like distributional matching. So I think it's a very interesting direction. I think like it's hard. I don't know. Yeah, I'm curious like how easy it is to do because of like the stability of estimating things like the standard deviation, and expected representations when like most nodes in our networks are like low degree, as well as things around like approximate Gaussianity of these distributions, like how well they actually do any kind of centering, of the node representations. But yeah, it's an interesting direction to think about. And then we also might want to reduce training discrepancies for GNNs between like low and high degree nodes. And we see that like it's very dependent on the choice of filter. So I think there's a lot of work to be done on like maybe some kind of like more flexible filter. I mean, I think there's a lot of people have been doing like flexible filter design. Obviously, people are like learning filters on the fly. Like GAT is like one of the primary, GAT is one of the primary examples of that. But I think like we can do some more maybe interpretable learning slash like tuning of these filters to maybe get to a place that's somehow maybe between like the random walk filter and the symmetric filter. Like this like exponential kind of like tuning we can do on like the node degree, for example. So we like have maybe not as much of a pronounced disparity in magnitude of representations, but we also kind of don't have or terrible discrepancy in the variance, of the representations. So some possible future directions. We didn't address possible sources of degree bias related to nonlinear activations, right? Like all the models we studied theoretically were linear. And I think the other thing too that I didn't mention here, is that whenever you have bounds, there's always a region of like your space that like you don't know what's happening. Like you kind of have a sense of like where things fall, but I really have been like re recently, and I cited myself here. So I'm like been really recently into thinking about precise theories, on why this stuff happens. So maybe like oftentimes this kind of precise analysis becomes more possible in high dimensions. The analysis becomes more tractable. So a high dimensional analysis of degree bias with nonlinear activations could be really interesting. Free probability theory is a really exciting tool, which I'm not going to get into here, but if you want to read more about it, the paper is in my references. Empirical validation wise, we only validated our findings on undirected and often, not often, like on only directed and homogeneous networks. And there is a lot of work to do to see like um, how prevalent degree bias is for directed networks, which I know that people don't tend to avoid within graph learning and heterogeneous networks. And heterogeneous networks, especially things like knowledge graphs, I think it'd be really cool to understand the implications of degree bias for knowledge retrieval from knowledge graphs. And yeah, again, a precise and systematic analysis of the training time bias dynamics of GNNs, and LLMs. Make that connection in a second, but I think there's more work to be done empirically on like how the training time dynamics of degree bias looks. So yeah, I think like not everything needs to involve LLMs. I don't personally think so, but like I want to highlight this connection for people who maybe are working on LLMs and are like don't know how relevant GNNs may be. So I think mechanistically, I view transformers as GNNs where graph filters are multi-head attention. So we can actually think of our sequences in when we're doing transformer stuff as a graph where the nodes are tokens and the attention between every pair of nodes is like edge weights in a graph. So it's a complete graph where we have different edge weights that correspond to like how much, for example, like this attends to sentence or sentence attends to also. And the interesting thing here is that GPT, like the random walk filter, GNN, and the GAT architecture all have row stochastic filters. Like they all have row normalized matrices, right? Like for the attention, like the canonical attention matrix in transformers, we're applying softmax to every single row. And so all the rows sum to one. And it's a probability distribution. Each row basically represents a probability distribution. And so we can often think of like tokens that receive less attention as low degree nodes. And maybe that means that like underrepresented tokens in pre-training corpora, for example, like neopronouns, like refer to individuals like trans, especially trans and non-binary individuals, can have like we can maybe more systematically or theoretically understand how those tokens get suppressed or like other tokens don't pay attention to those pronouns via the theories that we've and empirical understandings of degree bias that we've developed in the GNN setting. Yeah, so I just want to also give a shout out to my paper co-authors, Jian Kang and Yizhou Sun. And yeah, they're both so amazing. I like can't emphasize how amazing it is to work with them. Some references, and yeah, thank you. I'm happy to answer any questions.